So in class so far, we've covered intermolecular forces, but only for a pure substance. So now we want to discuss how do intermolecular forces affect solutions. So solution is like a mixture of different compounds, substances. So not a pure substance anymore. We got a mixture of methanol and water, or methanol and ethanol, or sodium chloride dissolved in water. We want to look at how does intermolecular forces come to play here. Okay. So we can first want to think about this with regards to how do they interact. Okay. So for example, we're going to look at a liquid-liquid interaction. So we have a liquid of one substance and a liquid of another substance. So let's say, for example, in one of these beakers, we just have water. Okay. And in another beaker, we have ethanol. Okay. So if we're looking at the intermolecular forces that are present within this, we'd see, well, we have the water attractions. Okay, well, those things are attracted to each other primarily by hydrogen bonding. Okay, over here we have methanol, and in our methanol we would have the methanol attractions. Okay, and so when they're separate, these are the attractions they would have. Again, it has this oxygen bonded to a hydrogen. So this also has the ability to have hydrogen bonding when it undergoes attractions between methanol molecule and another methanol molecule. Well, then we go ahead and let's go ahead and say, well, we pour methanol into the water beaker. So now in our beaker, we have water and methanol. And so we want to look at, well, what's different between these two scenarios? We have hydrogen bonding. And so now the new force that's present that we can have is the attraction of water to ethanol. Okay. Well, both of these have the ability to undergo hydrogen bonding. And so we see, well, then they can undergo hydrogen bonding. Okay. So now once we mix these together, we can see they have similar strengths of the attractions between the individual separate pure substances and the mixture. Okay? When we get to this where there's similar strengths of the attractions between water and water, ethanol and ethanol, water and methanol, they're both all hydrogen bonding. When they have similar strengths of attractions, it would make sense that these things would go ahead and mix together. Because when they mix together, we're going to have to think about, well, we're breaking these attractions between water and methanol in order to form these new attractions between water and methanol. So if something is going to take, a process is going to take a lot of energy to make that happen, we don't really have strong attractions here, we're not going to get this mixture to form. Well, these things have similar attractions, so that we'd have not the same, but similar strengths of attractions between our initial place and our final mixture. Okay? When we have this occur, these two substances will mix, and we call those two substances miscible. Okay? So if they're miscible, they will mix together. Now let's go ahead and say, instead of now we have water and methanol, what if we have water? So again, we have water and water, okay? And then in another beaker, we would see maybe we have hexane. Okay, so we have hexane. So now this is a nonpolar molecule. Here we have hydrogen bonding. Here we have nonpolar. So the strongest attractions that we would have would be our London dispersion forces. Okay, remember, these are weak attractions. These are very strong attractions. And so now we go ahead and we add these together. Okay, once we add them together, now the new type of attraction that can form would be the attraction from one of our water molecules to a hexane molecule. So this would be our hexane molecule, and it being attracted to our water molecule. Okay. Now when this is happening, this is going to be weak, right? This is no longer hydrogen bonding. Okay, this would be like a form of London dispersion force. It's very, very weak. Okay, so now what we've done is we've broken the attractions between these two, and now we're saying, water, you can't hang out with another water molecule. Now you got to hang out with a hexane molecule. Well, it's not going to want to hang out with a hexane molecule because these are weak attractions. It's adding potential energy to the system by taking away these attractions. It doesn't want to do that. Okay, and so if we start with something that has strong net, right, both of our mixtures together, and then we end up with weak attractions or intermolecular forces, well, notice that it's not going to want to do that. It's not going to want to, water's not going to want to stop hanging out with water to go hang out with hexane because there's not a really good connection or strength of attraction between those. So these will not mix together, and we can call that immiscible. Okay? So things that are immiscible are not going to mix together. So what does that look like with regards to something that's miscible? Well, if we took water and methanol together and we go ahead and we mix them, we would notice that it would just be all mixed together. Whereas if we had something like our hexane and water, when we tried to mix those two together, we're going to notice two distinct layers. We're going to notice our water layer and a hexane layer. They're not going to want to mix together. This is like salad dressing, right? Oil and water. Our hexane and water is not going to want to hang out together, so therefore they're not going to mix together, and they're going to separate out into two distinct layers. This would represent something that's immiscible, and this would represent something that's miscible. Okay, so now in our next video we're going to look at not just liquid-liquid, but what happens if we take a solid and try to dissolve a solid into a liquid and look at how intermolecular forces change there when we have those types of situations for a solution.